Hi, so this will be a short video to show you the parts of the springs and oscillation lab. Um, so this lab is basically in two parts, and the first part is we're going to measure K, and what K is the spring constant. So springs are something that we're getting into in Chapter 7 when we talk about work, and kind of the picture that we have is you imagine an object or a block attached to a wall via a spring, and if you were to stretch that spring, pull that block away with some force, the spring is going to pull back. And it turns out that this spring force is negative, so it's pulling back. It's called a restoring force, and it's proportional to the distance that you pull it. And for now, I'm going to call this delta x because you can think of this as the change in x from where it's starting from. And we usually call that starting position the equilibrium position. So what we're going to do for the first part of the lab is basically you're going to set up a hook that's hanging from a spring, and you're going to add mass to it so that it hangs down farther. And you're going to do this for different mass values. And what's going on in each of these situations is, let me do this in some different colors here. In each situation, you have the weight hanging down, and the weight is getting larger as you add mass. And the spring force is getting larger as it stretches. So you kind of get the idea here. And so they're balanced insofar as I can draw arrows that are the same size. These forces will be the same when it's hanging in equilibrium. So maybe we could just give these some numbers to distinguish them. And what you're going to do is just record that for some different values and make a plot of the force in newtons as a function of this distance. And notice it's going to look like this. It's going to be proportional to the distance, and the function that should look like, we should get a line. And depending on how you set this up, if you subtract off the initial height, then this would start from 0, or it might start somewhere else. The main thing being that the slope tells you k, the spring constant. And this has units of newtons per meter. And you can think of this as telling you basically how stiff the spring is. So let me show you a quick video clip that kind of shows you what this looks like in the lab. Hi, so the purpose of this little clip is just to show students what was done in the spring and oscillations lab. So the lab is in two parts, and the first part is to demonstrate measuring the spring constant, looking at Hooke's law. So what students, what they have is a spring that's hanging from a hook, and then we have a little hanger that's on the spring, And students we add mass to this. And as you add mass, the spring will be stretched and hang down farther. And we would record the position on the meter stick. And this allows us to measure Hooke's law. So the amount of displacement times the spring constant is going to be equal to the amount of weight that we've added to the hanger. So, and by plotting that data, you can extract the spring constant. So a couple other details. I noticed an error here. This in general is known as Hooke's law. This relationship between how springs work. Now, and notice this is a force that's a little bit different than what we've dealt with before in that it depends on the distance. So it's not a constant like we've been working a lot with gravity near the surface of the Earth. It depends on how much you stretch it. And then one other thing I would note is that in addition to the slope, you can get delta K from your regression analysis. We'll do that as well. Okay. So the second part of this lab, we're going to look at oscillations. So the first part was just manually measuring K by looking at a stretched spring. The second part is to consider oscillations. So what you're going to do is set the system in motion with different amounts of mass and see how it behaves. Before we look at that, let's take a second and talk about the math. So I told you that this spring force and kind of the cartoon picture that we had was a block on a spring. It would have some mass. This spring would have some K, etc. That this force due to the spring would look like negative Kx. And we know from Newton's second law that that force is equal to the mass times the acceleration of an object. Once you set it in motion and it starts moving, accelerating. And we can just as soon write this acceleration as a derivative. It's equal to second derivative of x with respect to time. Now, this expression, let me just write this a little bit differently. You have something that says that the derivative of x is equal to negative k over m times x. So think of this x as a function of time. Basically, we have an equation that contains a function and its second derivative. This is a differential equation. And we're going to solve this, or look at the solution to this, how a physicist often solves a differential equation by checking and verifying that a solution fulfills the equation. So there are different solutions for this, but a really simple one is to just think about sines and cosines. So for example, let's just pick an x of t. Let's try x of t equals a cosine omega t. Okay. So let's look at this. What would the first derivative of this be? We would have a times negative sine omega t, and we would pick up a factor of omega. We took the next derivative, second derivative. What we have, we would keep our negative sign, we would keep a, this sign would become cosine again, and we would pick up another factor of omega. So in other words, this would be negative omega squared a cosine omega t. So notice this function works. We recover the function. Here's our x again. And what this also means is that omega squared has to equal k over m. So what we can do is we can use this to relate the period to the spring constant and the mass. So what is omega exactly? Well, think about this. The trig function has to have an angle as an argument. And if you have omega times time, that must mean that the omega has units of angle per time, so that the argument is angle. So in other words, this has units of radians per second. So it is 2 pi times the frequency in hertz. And that's telling you that for one cycle, you're making 2 pi an angle. You're going all the way around the circle. And so what we can do is we can say, okay, let's take a square root of both sides of this. Omega then would be the square root of k over m. And we just said that omega is 2 pi f. And the frequency, so per second, we can relate to the period by noting that the period is 1 over the frequency. So actually, let me write this a little bit neater. So this would be 2 pi f equals root k over m. So in other words, the frequency would be 1 over 2 pi root k over m. And the period is 1 over the frequency, would be 2 pi root m over k. So this is our expression for the period. And, well, what does this mean? We have come up with this just by checking a solution to this differential equation based on Hooke's law for the response of a mass attached to a spring. And that period depends on the mass, and it depends on the spring constant. If you were to make the mass larger, we would expect the period to get longer. It would be oscillating more slowly. And if we were to make the spring constant bigger, i.e. if you were to use a stiffer spring, we would expect the period to get smaller, the thing to oscillate faster. And, you know, something else to notice, notice A, the amplitude, does not appear in our period expression. So it's not going to depend on the amplitude within reason. If you were to stretch the spring, you know, so much that it's no longer a spring, then Hooke's law is no longer going to hold. You know, in this case, the spring force would probably no longer equal negative kx. But if you were to use relatively small displacements, it's going to. What else did I want to mention? So that's basically the theory. What you're going to do is you're going to record data. You'll record a number of oscillations and measure the time for some number of oscillations. So if this is time and n oscillations, then you can get the period will just be that time divided by how many oscillations. And what we're going to do is we're going to create a plot with this as well. So you could plot the period directly. Let me put it over here, actually. You could plot the period directly and you would see this as a function of m. You would see this square root of m over k dependence. The other thing that we can do is we could reorganize this, solve this expression for m. If you do that, is, let's see, t over 2 pi. Notice we'd have to square everything, so this would become t squared over 2 pi quantity squared times a factor of k. This becomes stuff times t squared. So what you can do is you can create a plot where you plot it as a function of t squared. And in that situation, the slope of this plot is k over 4 pi squared. And you can extract the slope by fitting a trend line and pull out k. So in that situation, k will equal the slope. Let me call it, I'll just write the word slope here, times 4 pi squared. And you could get also from this, the delta k as well. And what you can do then is compare this to what we got from part 1. So compare k. Let me write this a little better. To what we measured from part 1. And that's basically it. So we're going to look at stretching the spring, and then we're also going to set the system in motion and look at the period of those oscillations as a function of adding mass and see how that changes. And then we can plot this, force this into a linear plot and extract the k as well and compare it to what we got from the first part. So in the second part of this lab, what students would be doing is studying this, instead of the static case where we just have the weight that's balanced by the spring force, we set the thing in motion and study oscillations. And we can examine how the oscillation period, the amount of time it takes to make one oscillation, depends on the mass and the spring constant. And if we take some data for different masses, we can extract from that the spring constant and compare the spring constant derived from studying the oscillations to the spring constant that we got just looking at Hooke's law. So how students would take data is either with a motion sensor in the computer, record the position of the hanger as it oscillates in time, or record some number of oscillations with a stopwatch, and then divide that number, that amount of time by the number of oscillations, and that would also yield the period for an oscillation. So just to give you a sense of what this data would, kind of what the situation would look like, the case without any mass, and then we can compare that oscillation to the case where we have added on our 80 grams again. It's going to hang down. And we would, students of course would record data for all the intermediate masses up to 80 grams. And then from that set of data we can extract the period, we can get the periods, and then from those periods we can examine the data and pull out the spring constant and compare this to what we got in the first part of the lab.